Hi students. So from the first 4 classes we have learned that complex functions and complex differentiation and construction of multi-functions and complex integrations. In the complex integration in the previous class we learned that how to integrate when the function is complex function is given over the curve and over the Cartesian coordinates if supposed to be mentioned in the integration. And now I will take that one more different types of problem. So in this problem we have seen that evaluate that integral over the limits 0, 3 to 2, 4 2y plus x squared into dx plus 3x minus y into dy along there are two curves which is given over which we need to integrate this function. The parabola, it is in parametric form, x is equal to 2t and y is equal to t squared plus 3, and one more curve that the straight line from the point 0, 3 to 2, 4. So here we first case that we have to integrate this function over the curve, the parabola x is equal to 2t and y is equal to t squared plus 3. So we need to find out the limit for either x and or y. So by using this parametric function. So to find out the limit for x and y, that is I want to replace this because this integrand is a function of two variables y and x. Now we have to reduce this to a single independent variable, that is t. So for value of x we need to find out what is the value of t, and for value of y we need to find out that value of t. Here x is varies from 0 to 2, therefore when x is equal to 0 t is 0, when x is equal to 2 when t is equal to 1. Similarly y is varies from 3 to 4 in the integrand, so integral, therefore when y is equal to 3 this t is equal to 0 and y is equal to 4 t is equal to 1. So here we observe that t varies from 0 to 1 as both x varies from 0 to 2 and y varies from 3 to 4. So therefore when x is equal to 2t, dx is equal to 2 dt, y is equal to t square plus 3, dy is equal to 2 t into dt. Substitute this in the integrand, so we get that, so 2 times of t square plus 3 plus 4t squared 2 into dt plus 6t minus t squared minus 3 2t into dt. So then observe here that all the terms in the integrand is function of a single variable t. Therefore this limit x and y is replaced by the limit t is equal to 0 to 1, and then this convert into that ordinary real valued function in t. So integrate this one. After integration we are applying the upper limit and lower limit, we get that 33 by 2. So this is the integration, the value of the integration of the given function along the curve, the given function, that is the curve is along the parabola x is equal to 2t and y is equal to t squared. Now we have to integrate the same function along the curve, the straight line from the point 0, 3 to 2, 4. Here we have observed that x is varies from 0 to 2 and y is varies from 3 to 4. But in the previous problems we have observed that x is constant or x is equal to 0 or y is equal to constant or y is equal to 0. In that situations we simply take that x is equal to constant means the corresponding derivative will become 0. But here both the variables are varied from 0 to 2 and 3 to 4. Therefore we need to find out a line joining these points. As usual, that simple equation y minus y is the equation for straight line. From that we get that x is equal to 2y minus 6 or y is equal to 1 by 2 x plus 6. Here it is our choice that we can convert that integrand to the function of a single independent variable, say either x or y. So I choose that to take that that integrand will become function of x. So I am taking y is equal to 1 by 2 x plus 6, therefore dy is equal to dx by 2 dx by 2. So substitute in this and then say that this integrand is function of x, therefore x is varies from 0 to 2. In that case I got all the terms by replacing that y is equal to 1 by 2 x plus 6. I get here this term, and then after simplification I get this term. Then totally this is a function of x and constant, therefore integrate with a normal integration. We get that after applying the limits we obtained 97 by 6. So we have observed that in the line integral there are suppose that parabola that any parametric functions are given, that will be converted into a single independent variable. If that any two different limits is given, in that situation also we have to convert that integrand to the function of single real valued function, and then we have to integrate. So that is that's all about the line integrals of the complex variables. Now we have passed on to the theorem, one of the important theorem in the complex analysis, that is Cauchy's theorem. The Cauchy's theorem states that if f of z is analytic function and f dash z is continuous at all points inside and on a simple closed curve, then that integral over the simple closed curve C f of z dz is always equal to 0. So I just recall this definition, analytic function. F of z is analytic means then we know that a function, complex function f of z is differentiable at any point in the complex plane, then it must differentiate that neighborhood of that entire neighborhood of that point E. So then only we can say that f of z is analytic. At least one point in which at which it is not differentiable in the neighborhood of a point where the function f of z is analytic. In that situation, that differentiability does not exist, or differentiability exists but it is not analytic function. So now I see, before taking the proof, just I have taken simple closed curve like this in the complex plane. So here that this is that region bounded by this curve, and see that f of z is analytic inside and as well as on this curve. Then as usual f of z is represented by u plus iv, and z is, we know that is a complex number x plus iv, dz is equal to dx plus I dy as usual. Then the integral over the curve C, closed curve C, f of z dz is equal to, then after simplification of this one we got it u dx minus v dy plus I into integral over the curve C v dx plus u dy. So here the given curve in the complex plane is a simple closed curve. So now we use the definition of Green's theorem. That Green's theorem states that the line integrals m dx plus n dy, so m is a function of x and y, n is a function of x and y along the curve C, then which gives that convert into surface integral dou n by dou x minus dou m by dou y dx into dy, where A is a region bounded by the curve E. Applying this theorem on RHS of 1, we obtain here, that is u dx m dx minus m dx plus n dy, here m dx plus n dy form. So here if I apply this Green's theorem, we are getting that dou by dou x of minus v minus dou u by dou y dx into dy. So because f of z is it is enclosed by a region, this function C A is a region enclosed by this curve, so therefore the statement is valid for this case also. So dx by dy and plus I into surface integral A dou u by dou x minus dou u by dou y dx into dy. So now the complex real and imaginary part of complex function is transformed as per the Green's theorem statement. We got this term. Since f of z is analytic, we have Cauchy's Riemann equation dou u by dou x is equal to dou u by dou y. So dou u by dou y is equal to minus dou u by dou x. This is a Cauchy's Riemann equation since Cartesian form. Using this in the above integral, we got that minus dou u by dou x plus dou u by dou x and dou u by dou x minus dou u by dou x. So these two are get cancelled, these two are get cancelled, therefore we get that finally 0. So integral over the simple closed curve C of a complex function f of z dz is always gives 0. This proves the Cauchy's theorem result. So this Cauchy's theorem gives that many applications to find out that integration of a complex function. If the extension of this Cauchy's theorem is like this, if f of z is analytic in the region D between two simple closed curves C and C1, then that integration along the curve C f of z dz is always equal to integral along the curve C1 f of z dz. So here very simple, the proof is briefly explained by taking the graph. So that outer curve is a curve C and inner curve is a curve C1, and you see that as per the, from the definition f of z is analytic in this region D. So and in this region, and we are seeing that it is also analytic on the curve C and on the curve C1. To get the result, to prove these results, we need to introduce that a cross cut AB. The cross cut means I can take that by using this one cut. If I apply here, then we can we can partition this region into this form. Here we observe that this curve is having that orientation towards the positive orientation like this, and then here inside also I have taken the positive orientation like this. Now the curve is cut. After cutting this one, this is AB and this is AB. One cut we have seen that gives that two sides, and these two sides is this, and here I have taken this complex function f of z which is analytic in this region as well as on this the line on the curve C and line on the AB and line on the curve C inside curve C1 and then this BE. So therefore this I can obtain here. Now f of z is analytic at all points inside and on a simple closed curve. The curve C is this one. C is a union of C, that outer closed curve, union of a one cut AB, union of inner closed curve and another cut BA. By Cauchy's theorem, that integral over this entire union curve C f of z dz is equal to 0. So that integration along the union of this curve f of z is equal to dz means by the definition of the integral, this union can be written as integral along the curve C f of z dz, integral along the curve AB f of z dz plus integral along the curve C1 f of z dz plus integral along the curve BA f of z dz. So now, so here we are the curve is traversed in this direction and get inside from this side, and then this traverse opposite to this direction, and then it is come out of this one. This is positive direction means this is negative direction. This is also, this is positive means then this way if I traverse then it will be negative direction. So therefore I can get that the curve C1 is the traverse along the opposite, therefore minus C1. Again that it is BA, then that minus AB, it is in the opposite direction. So therefore integral along the curve AB and integral minus integral along the curve AB get cancelled, and this one, and finally we get that result f of z dz, integral along the curve C f of z dz minus integral along the curve C1 f of z dz is equal to 0, and this is equal to 0, hence the result. So this can be extended to introducing that the finite that there are n numbers of simple closed curves entirely lies in a big closed curve C. In that situation, we are seeing that the result will be as follows. If C1 and C2, C3 and Cn be any n number of closed curves within C, then integration along the curve C f of z dz is equal to integral along the curve C1 plus integral along the curve C2 plus integral along the curve C3 so on plus integral along the curve Cn f of z dz. And this result is very useful to find out the residues by using the Cauchy's residue theorem in future. So there we are using this concept to solve the problems. So examples which we have to take here, that one of the example is verify Cauchy's theorem for the function f of z is equal to z square, where c is the square having vertices 0, 0, 1, 0, 1, 1 and 0, 1. And we have seen that f of z is equal to z square. It's a complex function and it is analytic everywhere in the complex plane. Therefore, it is analytic within the square and also on the square. So, therefore, the analytic property of this function, that f of z is equal to z square, satisfies the analytic property, and it is also continuous because its derivative is also continuous in this region and also on the region. So, here these points are taken like this in the curve. So, first point it is 0, 0, O, and this traverse along this way it is 1, 0, and again if I take that point B 1, 1, and this curve if I take that one, this one, that is again this, then this is 0, 1, and this way you see that this function is, we are taking the square. So, now f of z is equal to z square, f of z is equal to z square is analytic within and on this curve, and we have taken this curve partitioned into the curve along OA is C1 and curve along AB is C2 and curve along BC, that is AB, BC is C2, C3, and then C2O is C4. Then this square we have observed here, the square is the curve C is a square having the points, these points is 0, 0, 1, 0 and 1, 1 and this one, and this curve that is taken, C is a union of C1, C2, C3, C4. I simplified this one in easiest manner of integration, that is that gives that is since f of z is equal to, as I said, that it is analytic everywhere in the complex plane, it is analytic at all points inside and on the curve C. By Cauchy's theorem, integral along the square, that is along the square curve f of z is equal to dz is equal to 0, and integral along the curve C z square dz is equal to 0. And because this is union of, the square is a union of the curve C1, curve C2, curve C3, curve C4, that classified in this as integral along the curve C, the integral along the curve C of a function z square dz is equal to integral along the curve OA and integral along the curve AB, integral along the line BC, integral along the curve CO. So, this is having the limit is for here, this is the limit, then 0 to 0. From this case, x is varies from 0 to 1 and y is equal to 0, therefore, dy is equal to 0. In along the line OA, the curve C1 is having this one. Here, in this case, x is equal to 1, therefore, it is dx is equal to 0 and y is varies from 0 to 1. In this curve, then here we have to observe that here x is varies from 1 to 0, that is x is varies from 1 to 0 and y value is constant. Here y is constant, dy is equal to 0 and x is varies from 1 to 0. And here in this case we observe that here what is that we have taken that y is varies from 1 to 0 and x is equal to 0. X is equal to 0 means it is dx is equal to 0 and y is varies from 1 to 0. So, from the curve figure we are obtaining the limits, that is 0, 0, 1, 0, 1, 0, 1, 1 and 1, 1 and 0, 1 and 0, 1 and 0, 0. So, here first case I have considered, take that the integral from the curve 0, 0 to 1, 0. As I mentioned in the figure, x is equal to, x is varies from 0 to 1 and y is equal to 0. This I am using here, and then apply this in integrand, that is x is equal to x plus I into 0 whole square dx. Then after integration I get that 1 by 3. So I call this one as 2, and then again consider the second integral. Second integral along the curve 1 comma along the line or along the line joining AB or curve C2, that is x is equal to 1 and y is varies from 0 to 1. X is equal to 1 means dx is equal to 0, there is no variation, it is because constant, and y is varies from 0 to 1. Now use these values, substitute x is equal to 1 and replace the limit as y is varies from 0 to 1 in the integrand, that gives 1 plus iy whole squared I dy. This integration gives that. After integrating this one we have to apply the limit. Finally I get that 2 by 3 I minus 1. So this simplification I am using this property 1 plus I squared is equal to 2i, and simple way we have obtained this value of integration is 2 by 3 I minus 1. Consider the third integrand. The third integral in that case, third integral is along the line BC or along the curve C3, the points are B1 comma 1 and points of C 0 comma 1. In this case y is equal to 1, dy is equal to 0 and x is varies from 1 to 0. So I use this concept. Here y is replaced by 1 and dy is replaced by 0 and x is varies from 1 to 0. Now apply this in this above integral, we get that x is varies from 1 to 0 and x plus I whole squared because y is equal to 1. So again after integration we get that minus I plus 2 by 3. After integration and simple calculations we get that minus I plus 2 by 3. So this is last line or last the path we are taken from C to 0, that is C to O, otherwise the curve C1. Along the curve C4 the limit is given 0 to 1 to 0 comma 0. Here we see that x is equal to 0, x is constant, x is not having any variation, therefore dx is equal to 0 and y is varies from 1 to 0, y is varies from 1 to 0, and this concept I use that in the fourth integral of the above integration. So that gives here x is equal to 0, dx is equal to 0, y is varies from 1 to 0. Substitute this in the above integral, we get that I y whole squared into I dy. Using this minus I and integration from y cube, therefore after that we get that I by 3. After simplify this one we get that I3. So now all the integrals of the RHS of the integral along the square z squared dz is obtained, and substitute all this on RHS of the above integral 1, we get that 1 by 3 plus 2 by I minus 1 plus 2 by I, this one and I, and this is the simplification. We can see that all the things are get cancels and then finally I get that 0. Hence Cauchy's theorem verified. If C is the circle, another problem here, if C is the circle mod z is equal to 1, verify the Cauchy's theorem for f of z is equal to z3. In the previous class, in the case of that line integral, we have proved this one, f of z is equal to integral of f of z along the curve mod z is equal to 1 is 0, that we have proved. And now another example I am taking here is show that integral along the curve C mod z whole square dz is equal to I minus 1, where C is the square having vertices and having vertices 0 comma 0, 1 comma 0, 1 comma 1 and 0 comma 1. Give the reason for Cauchy's theorem not being satisfied. Just now we have observed that the same square we have taken here for the function that is all the values are same thing. Here mod z whole square can be taken as it is mod z means we know that z is equal to x plus iy. Therefore, mod z is equal to square root of x squared plus I squared. So therefore mod z is equal to x squared plus y squared. So now I am going to replace this mod z squared is equal to z squared. The similar way of the previous problem, I have taken that integral along the square c mod z squared dz is equal to integral along the line ya, integral along the line ab, integral along the line bc, integral along the line co, or the curve c1, c2, c3, c4, because the curve square c is a union of c1, c2, c3, c4, and this gives all the integrals I have written in a single line. I go through that one. Integration along the line OA is the coordinates of limits are 0, 0, 1, 0, x squared plus y squared into dx plus I dy, because dz is equal to dx plus I dy. Similar way, all the limits how I have written in the previous problem, same way we have taken here. Then I use the same concept that because this is x is equal to 0 to 1, we observe that in the previous case x is equal to 0 to 1 means y is 0, therefore dy is equal to 0, I got x squared dx. And y is varies from 0 to 1 and x is equal to 1, therefore x is equal to 1 plus y squared I dy, dx is equal to 0, and limit y is varies from 0 to 1. And here that along the curve BC, the limit is x is varies from 1 to 0 and y is equal to 1, therefore y is equal to 1 and dy is equal to 0, that I got it x squared plus 1 dx. And the curve CO, we know that the curve CO, y is varies from 1 to 0 and x is equal to 0, I got this one. After simplification, after integration, we got that 1 by 3 I 1 plus by 4 by 3 minus 4 by 3 I by 3, therefore I got that I minus 1, that is the result is 1 minus 1 plus I, therefore it is I minus 1, it is not equal to 0. But simply we have observed that in the previous case z square along the curve c square, we have got that Cauchy's theorem is verified, but here Cauchy's theorem is not verified, because one of the reason is since mod z f of z is equal to mod z square is equal to x squared plus y squared, that is u plus iv is equal to x squared plus y squared is not analytic, because the necessary condition ux is equal to vy, that is dou u by dou x is equal to dou u by dou y, dou u by dou x and dou u by dou y, and dou u by dou y is equal to minus dou u by dou x are not satisfied. This is the reason for Cauchy's theorem not being satisfied, because this is one of the necessary conditions to be satisfied to say that the given complex function is analytic function. And one more important result here, Cauchy's integral formula. The Cauchy's integral formula is, you have observed that Cauchy's theorem is different from Cauchy's integral formula. The Cauchy's integral formula statement is as follows: if f of z is analytic within and on a closed curve C, and if A is any point within C, then f of A is equal to 1 by 2 pi I and integral along the closed curve C f of z minus f of z divided by z minus A into dz. This is the statement is clearly says that, observe that the statement is f of z is a function f of z is analytic in any simple closed curve C, any simple closed curve. Then the evaluation of this point, and A is in the statement, then point A is inside. If A is any point within C means I can take that point A is within the simple closed curve, and then we can find the value of the function f of z at a point A in the form of 1 by 2 pi I integral along the curve C f of z divided by z minus A into dz. So now proof is as follows: consider a simple closed curve with a point A inside the simple closed curve. Now consider an integrand which is given in the statement f of z divided by z minus A which is an analytic at all points within C, which is an analytic at all points within C except at a point z is equal to E. So, because this function f of z divided by z minus A, this is f of z is analytic on this curve and also inside this curve. If I take that ratio of this function f of z divided by z minus A, observe that this ratio is analytic on the curve and also inside the curve, but except at this point because function does not define. Then analytic property is violated at this point. So, therefore, for this case I have to take that one simple closed curve with the smallest radius. Take a circle with the smallest radius R inside this closed curve that I have taken as, with the point A as a center and radius R, draw a small circle C1 inside the closed curve which is lying entirely within C. Now observe that this f of z, the ratio f of z divided by z minus A being analytic in the region which is bounded by the curve C and also the curve C1. So, it is analytic on and inside the region bounded by these two curves, and this is the again that by extension of Cauchy's theorem we have seen that in the beginning of this class, that is integral along the curve C f of z divided by z minus A dz is equal to integral along the curve C1 f of z divided by z minus A into dz. That means this function, it is integral along the curve C1 is same as the same function integral along the curve C is one and the same. So, this is taken in this form for any point z on the circle in the inside the on the circle, this one, any point on this circle we can take that z minus A is equal to R, or this can be written as z minus A is equal to R into e power I theta. So, this is the one of the case we have taken here, and then simplify this one dz is equal to, because dz is equal to I into R into e power I theta d theta, because R is a constant, it is a smallest radius and constant radius we have taken, and z is equal to A plus R e power I theta. Now, theta is varies from 0 to 2 pi on the curve C1. On the curve C1 means that is circle C1. So, in the circle C1 where theta is varies from 0 to 2 pi. So, in this case along the circle we are integrating the function f of z divided by z minus A. Therefore, you replace z is equal to A plus R e power I theta, and replace z minus A is equal to R into e power I theta, and dz is equal to I into R into e power I theta into d theta. Then integration, that theta is varies from 0 to 2 pi. Then after simplification we obtain I into 0 to 2 pi. Here that e power I theta and R get cancelled, then you can take that I is a constant taken out from the integral, and therefore I get that 0 to 2 pi f of A plus R e power I theta d theta. Here this function is here this ratio complex function, this ratio function is defined even on this circle and also many point in the neighborhood of this point, but not at the point A. Therefore, we are taking the limiting case. Limiting case means we are shrinking this circle to the point A. That how this shrinking this circle to the point A means, take that limit R tends to 0 means the circle is come that near shrinking nearer to the point A. In this situation, existence of this one, I get that in the limiting form as the circle C1 shrinks to the point A, that is R tends to 0. that is r tends to 0 means then this function, the above line integral approach to integral along the curve, that is c f of z divided by z minus a dz is equal to I into that limit theta varies from 0 to 2 pi f of a to d theta. Then this gives that totally I am getting that f of a is equal to 1 by 2 pi I integral along the curve c f of z divided by z minus a into dz. So this shows that we can determine the value of the function f of z because it is analytic function everywhere in the, that is in the closed curve, and if a is a point inside, in that situation we can find out the value of the function f of z at a point a in the form of 1 by 2 pi I integral of the curve c f of z divided by z minus a into dz, which is the desired Cauchy's integral formula. By using this formula, so we can generalize this result, that generalized the Cauchy's integral formula as f dash a. That means if f of z is analytic function means the derivatives exist, and the value of the derivative of that complex function can also be determined by using the following generalized Cauchy's integral formula. It is f dash a is equal to 1 by 2 pi I integral along the simple closed curve c f of z divided by z minus a whole squared dz, and f double dash, and then we can finally find out the nth derivative of a function, complex function f of z at z is equal to a also determine, that is 1 by 2 pi I integral along the curve c f of z divided by z minus a to the power of n plus 1 into dz. In view of the solving the problems of the integral form, so we are using this Cauchy's integral formula in a simple manner, that is f of z, that integral along the curve c f of z divided by z minus a dz is equal to 2 pi I f of a if a is inside c, and that is equal to 0 if a is outside c. So here that if this point a, if you take that any curve, this point a inside, then I am getting the result that f of a is equal to that integral along the curve c f of z divided by z minus a into dz, it is always equal to 2 pi I into f of a. Suppose if this point is not inside, then suppose if it is lies outside, then what you say about this one? The complex function, the ratio of this complex function f of z and divided by z minus a is analytic on this curve and also inside this curve. Therefore, this satisfies the conditions of the Cauchy's theorem. Then if it is satisfied the condition of the Cauchy's theorem, then that integral is f of z divided by z minus a into dz is equal to 0 when a is a point outside the simple closed curve. So these results are very important to solve the problem. In this case, I have to take that examples to see that how we are going to get that result for this one. So problems on Cauchy's integral formula. One of the problem I have taken here is evaluate that integral along the curve c e power z divided by z plus I pi dz over each of the following regions c. The one region 1 is mod z is equal to 2 pi and mod z is equal to pi by 2 and mod z minus 1 is equal to 1. So here this problem is given e power z divided by z plus I. Evaluate integral along the curve e power z divided by z plus I pi into dz. Then this integral we have to taken that one of the case is mod z is equal to 2 pi. So then this integral, now if I take this integral as per our the case of I pi, I just rearrange this one as per the Cauchy's integral formula. I can take that f of z divided by z minus of minus I pi, z minus of minus I pi into dz. So see this term, I have written this term as Cauchy's integral formula, that is f of z is equal to e power z. Then one by one case we have discussed here. Here f of z is equal to e power z means we have observed that e power z is analytical everywhere in the complex plane. So, everywhere in the complex plane means the first case I have taken here is mod z is equal to 2 pi. See, this mod z is equal to 2 pi represents a circle centered at origin with radius 2 pi. Circle centered at origin with radius 2 pi means, then if you write that any circle, this is a circle mod z is equal to 2 pi, then this is origin. Then what is the radius of this is 2 pi. Then definitely e power z, the complex function f of z is analytic on the circle and also inside the circle. This complex function f of z, e power z is analytic on and inside the complex, that is inside the circle mod z is equal to 2 pi. But this ratio function e power z divided by z minus minus of I pi, if I take that, minus I pi is a point, here I can write this one. Definitely observe this, minus I pi lies inside the circle, mod z is equal to 2 pi. So, therefore, this results here I want to write that 2 pi I into f of minus I pi. F of minus I pi, because minus I pi lies inside the circle, then I use the Cauchy's integral formula to evaluate this integral, and this integral evaluation is equal to f of minus I pi. This is f of minus I pi is equal to e power minus I pi. E power minus I pi means cos I pi minus I sin I pi. So, cos I pi minus I sin I pi means it is minus 1. So, therefore, this is minus 1 means then I got that result, it is minus 2 pi I. So, that integral of the complex function over the circle mod z is equal to, this is over the circle mod z is equal to 2 pi, I got this result. This is the application of our integral, Cauchy's integral formula. Just I go through that, this one, it is a circle centered at origin and minus I, even plus I is also inside. So, if I take this one, now I got that minus 2 pi. So, everything that if A, here the point A is minus I pi lies inside the circle, mod z is equal to 2 pi, and f of z is equal to e power z is analytic within and on a circle, mod z is equal to 2 pi. Therefore, Cauchy's integral formula follows this result. Then another case which is given, mod z is equal to pi by 2. Mod z is equal to pi by 2 means, then definitely I have to take this result as pi by 2, and this will be pi by 2. What this means, that the mod z is equal to pi by 2 means, then curve I have to integrate this one along the curve mod z is equal to pi by 2. This mod z is equal to pi by 2 is a circle centered at origin with radius pi by 2. With radius pi by 2 means, this is a pi by 2 means the point minus I pi is this side. So, point minus I pi here and point plus I pi in the above, but it is not my concern, now I have to take a minus I pi. So, pi by 2 means this is the distance, definitely it is minus I pi. This is minus I pi by 2, and this is the point. Observe that this is a point which lies outside the circle mod z is equal to pi by 2. So, this point minus I pi is lies outside the circle mod z is equal to pi by 2, and f of z divided by z minus I pi is, that means this function is analytic on the circle and inside the circle. That means it is analytic at all points on the circle and inside the circle. Therefore, this result is as per the Cauchy's theorem, it is very simple result, it is equal to 0. So, this follows the second condition because the point minus I pi lies outside the circle. Now, one more circle we have taken, that mod z minus 1. Mod z minus 1 is equal to 1. Mod z minus 1 is equal to 1 means it is a circle center at origin 1, 0. it's a circle center at a point, complex point 1 means then this is a circle, its origin, and this center at the point origin 1 and radius is, that is I have taken the distance is 1. Therefore, this circle is this one. Then definitely, so you have observed that this point minus I pi is lies here and this point minus I pi is plus I pi is also lies here. Then what is then this is also 0, we got it, and here also we see that same argument which follows here also, because we have to observe that the point minus I is lies outside the circle mod z minus 1 is equal to 1. That means the radius is 1 and center at a point 1 comma 0. Therefore, this minus I pi lies outside this circle means then again we are using the concept of the Cauchy's integral formula. This ratio is analytic on this circle and also inside the circle. Therefore, by Cauchy's theorem this result will become 0. That result will become 0 that I have written here, that is again mod z minus 1 is equal to 1 is a circle center at the point 1 comma 0 and radius 1. Then here in this case that same procedure which follow here to get that result 1. One more problem, evaluate using the Cauchy's integral formula, that evaluate using Cauchy's integral formula. Number 1, integral of e power 2z divided by z plus 1 z minus 2 dz, where c represents the circle mod z is equal to 3. So here this function is having the denominator we are having factor of 2 terms z plus 1 and z minus 2. We have expressed this function as per our Cauchy's integral formula. Therefore, I have taken f of z is equal to e power 2z. Again e power 2z is analytic everywhere in the complex plane. Therefore, 1 by z plus 1 by partial fractions we can obtain, that is a value is this one and b value. Then if I get that 1 by 3 into 1 by z minus 2 minus z 1 divided by z plus 1, substitute in the integrand and RHS of the function, I got that integral over the curve c f of z 1 by 3 z minus 2. So this after simplification I get that 1 by 3 into f of z divided by z minus 2 minus f of z divided by z minus 1. Z minus of minus 1 here, that is z minus of minus 1, and this I can mod z is equal to 3 is a circle, mod z is equal to 3 is a circle, and then see that both the points where these points are lies, and then it is also very simple. Mod z is equal to 3 is a circle center at the origin with radius 3, r is equal to 3. Therefore, this distance is 3 comma 0 and this distance is minus 3 comma 0, and therefore here we have to observe that here z is equal to minus 2 means that point A is equal to plus 2, point A is equal to plus 2, and here the z minus of minus 1, this is minus 1. So, z is equal to point A is equal to minus 1 is lies here, A is equal to point lies here minus 1. Observe that both the point minus 1 and 2 are lies inside the circle mod z is equal to 3. So, therefore, using Cauchy's integral formula we can express this result as this is f of z. Therefore, it is both the points lies inside the circle. Therefore, it is 1 by 3 into 2 pi I f of 2 minus 1 by 3 into 2 pi I f of minus 1. After simplification, I got that e power 4 and e4. The expression, that same thing we are expressed here, that all the points of this function, and therefore, we both the problem we observe that is the point lies inside the closed curve. Then we have result that 2 pi I into f of that point, and if its point lies outside, definitely that integral will become 0. I think that today I stopped up to this stage. Next session I am going to take up that residues, poles and singular points, and isolated singular point, removable singular point, and here we observe that Cauchy's theorem and Cauchy's integral formula, it's very important. It's very important means that it is having important types of problems can be solved by using this property. So, I stop at this stage. Next class I will continue.